Batch normalization, introduced by Sergey Ioffe and Christian Szegedy in 2015, has emerged as one of the most influential techniques in deep learning, fundamentally altering how neural networks are trained. Its core idea is deceptively simple. Normalize the activations of each layer so that they maintain a stable distribution throughout training. This innovation addresses several long-standing challenges in deep neural network training, including slow convergence, internal covariate shift, overfitting, and instability. By carefully examining the mechanisms and effects of batch normalization, we can better appreciate why it has become a standard component in modern neural architectures. At its heart, batch normalization seeks to mitigate the problem of internal covariate shift, the phenomenon where the distribution of inputs to a given layer changes as the parameters of the previous layers are updated during training. This shifting input distribution forces each layer to continuously adapt to new distributions, slowing down the training process and making deep networks harder to optimize. Batch normalization counters this by standardizing the inputs to each layer, ensuring that they have zero mean and unit variance within each mini-batch. Mathematically, for each activation in a mini-batch, the mean and variance are computed, and then the activation is normalized. To preserve the network's representational power, two learnable parameters, gamma, scale, and beta, shift, are introduced, allowing the network to recover the original activations if needed. One of the most immediate and noticeable benefits of batch normalization is the acceleration of training. By keeping the distributions of layer inputs more stable, batch normalization enables the use of much higher learning rates without the risk of divergence. This is because the normalization process reduces the sensitivity of the network to parameter initialization and learning rate selection, both of which can otherwise lead to unstable or slow training. Furthermore, batch normalization acts as a form of smoothing on the loss landscape, making it easier for gradient-based optimizers to find effective paths toward minima. Empirical evidence consistently shows that models with batch normalization converge in fewer epochs and often achieve better performance than their non-normalized counterparts. Beyond speeding up convergence, batch normalization also plays a significant role in improving model generalization and reducing overfitting. Although the primary purpose of batch normalization is not regularization, the stochastic nature of computing statistics over mini-batches introduces a form of noise into the learning process. Each mini-batch provides slightly different estimates of the mean and variance, leading to small fluctuations in the activations during training. This noise acts similarly to other regularization techniques, such as dropout, by preventing the network from becoming too reliant on specific activations or pathways. As a result, models trained with batch normalization often require less explicit regularization and can achieve comparable or superior test accuracy even when trained on complex datasets. Moreover, batch normalization enhances model stability in several important ways. Deep neural networks are notorious for issues such as vanishing and exploding gradients, especially as the number of layers increases. These problems arise when gradients become excessively small or large, as they are propagated backward through the network, making it difficult to update weights effectively. By normalizing the activations at each layer, batch normalization helps maintain a consistent scale of gradients throughout the network. This consistency not only alleviates issues related to vanishing or exploding gradients, but also enables the successful training of much deeper architectures than was previously possible. Another subtle yet crucial impact of batch normalization is its effect on parameter initialization. Before batch normalization, careful initialization strategies were required to ensure that the signal propagated through the network without diminishing or blowing up. With batch normalization, the network becomes less sensitive to the choice of initial weights, since the normalization process corrects for poor initializations by standardizing the activations early in training. This robustness simplifies the design and tuning of neural networks, lowering the barrier to entry for practitioners and enabling more rapid experimentation. Batch normalization also interacts synergistically with other components of modern deep learning pipelines. For instance, it allows for the use of saturating nonlinearities like sigmoid and tanh, which were previously avoided in favor of ReLU due to their tendency to cause vanishing gradients. With batch normalization, these nonlinearities can be used more effectively, potentially expanding the design space for neural architectures. Additionally, batch normalization has been shown to reduce the need for certain forms of explicit regularization, such as dropout, especially in convolutional neural networks. This is because the mini-batch-induced noise and improved stability already provide significant protection against overfitting. Despite its many advantages, batch normalization is not without limitations. Its reliance on mini-batch statistics can be problematic in certain scenarios, such as online learning or when batch sizes are very small. Small batches can lead to noisy or unreliable estimates of mean and variance, reducing the effectiveness of normalization and potentially harming performance. In response, alternative normalization techniques such as layer normalization, instance normalization, and group normalization have been proposed for specific contexts, such as recurrent neural networks or style transfer tasks. Nevertheless, for most feed-forward and convolutional architectures, batch normalization remains the default choice due to its simplicity and effectiveness. The impact of batch normalization extends beyond mere performance metrics. It has fundamentally changed how researchers and practitioners approach network design and training. By alleviating the need for painstaking tuning of learning rates, initialization schemes, and regularization strategies, batch normalization has democratized access to deep learning, making it more accessible and reliable. Its widespread adoption in state-of-the-art architectures, from ResNets and inception networks to transformers, attests to its value across a broad range of applications. In conclusion, batch normalization represents a pivotal advancement in the field of deep learning, addressing critical issues related to training speed, overfitting, and model stability. By normalizing layer inputs within mini-batches and introducing learnable scaling and shifting parameters, it accelerates convergence, enhances generalization, and stabilizes deep networks. While not a panacea for all training challenges, its influence is undeniable, shaping the evolution of neural network research and practice. As deep learning continues to evolve, techniques like batch normalization will remain central to building robust, efficient, and high-performing models.